Welcome to RBR's Introduction to Sensor Technology. My name is Jon Taylor. I manage a team of engineers here at RBR, and we work to develop new sensors and integrate sensors from other manufacturers. Today, you'll be learning about a selection of common oceanographic sensors and the parameters they help to measure and the basic operating principles behind each sensor. If you have any questions today, please add them to the Q&A and we'll answer them at the end of the webinar. All right. Go. All right, so today we will cover these various sensors here, which measure the following parameters such as temperature, pressure, conductivity, and a variety of biogeochemical parameters. The first one is temperature. So this plays a key role in investigating ocean circulation and climate change. To measure temperature, we use a thermistor. At RBR, we use age glass thermistors. These are very stable and thus have a very minimal drift on the order of 2 millikelvin per year. We use particularly negative temperature coefficient thermistors, where the resistance decreases as the temperature increases, which is kind of indicated by this plot over here on the bottom right. And this is characterized using the Steinhart-Hart equation, which converts our raw voltage into a temperature in degrees Celsius. So we offer a variety of temperature sensors. They come in a few different designs. They all have roughly the same accuracy and same range from -5 to 35. And they differ mostly in their time constant, which is due to the construction of the sensor. And they're all rated up to 10,000 meters. So I have a few of them here. You can see this is one of our fast, where you can barely see the thermistor there. It's a very thin thermistor made out of stainless steel. This responds very quickly to any changes in temperature and is ideal for any profiling application. If you want something a little more robust, we have this design here, which is a little thicker, made out of titanium. Still fairly quick to respond. It takes about a second, but much better for longer term deployments. If you want to go very deep and have a very robust design, we have this one here, which we call the Abyssal. The thermistor is embedded in this giant slug of titanium here, and this you could throw into the bottom of the Marianas Trench and have no concern of it ever leaking. And oh, one moment. There we go. So in addition to the regular thermistors, most other parameters or sensors that RBR manufactures use temperature for some form of compensation. And in fact, all of the sensors I'll talk about today use a thermistor in some form or another to compensate its reading. So next up is pressure. So we measure pressure as it's a key parameter to drive depth, and it's also used for the compensation of other sensors, but also the derivation of quite a few other direct parameters. There are two primary technologies for measuring pressure. The most common is a piezoresistive, and the other is a quartz crystal resonator, which is has a very high sensitivity and great for certain applications. So a piezoresistive sensor, it measures the resistance across the sensor. And this resistance increases as the pressure on the internal crystal increases. And these sensors are kind of the industry standard. They provide a rapid response to changes in pressure, and they can operate across a large variety of pressures and temperatures. Here I have a couple different designs of them. The construction is quite similar. They differ a little bit in sort of the diameter and the materials that are used. The main difference for the very deep rated units versus the shallow rated unit, it actually lies in the crystal inside. So changing the thickness of that particular crystal, it changes the sensitivity to pressure. And they're quite robust. The damage one can do to these sensors is essentially if you've damaged the membrane. So as you can see, there's these concentric rings and where the membrane meets the housing, if there's any dents to the membrane or any fouling or crevice corrosion that happens on those, that's where the performance of the pressure sensor might change. But these are both constructed of materials that don't corrode in seawater, so should never be a problem with these, but something to keep an eye out for. Oop, too far. The next one is pressure tech is the quartz crystal resonator. These come in sort of two forms, one for low pressure, which is sort of 330 decibars or less. In this scenario, it's this image here. I don't know if you can see my cursor, but where pressure acts on a bellows, and this bellows generates a force and torque about a pivot point and compressively stresses the quartz crystal. And in the high pressure version, the pressure acts on a bourdon tube, and it applies a tension on the quartz crystal. And this is the technology that's used for the higher pressure one, sort of 2000 decibar to 10,000. The application of compression or tension force on the quartz crystal changes the resonance frequency of the quartz, and this is then translated into pressure. And these sensors are particularly stable over time, however, they're quite costly. The breakdown of sort of the key differences between a piezoresistive and a quartz-based sensor mostly lies in the resolution. As you can see, the resolution is 1,000 times better in the quartz application, and also in the drift, we're many orders of magnitude quite more stable. So it certainly has some unique applications for that type of technology. Next is conductivity. So we measured conductivity to see how many dissolved substances, chemicals, and minerals are present in the seawater. These minerals and chemicals come from runoff from the land, as well as sort of volcanic and geological activities. And from conductivity, the most common parameter that one derives is salinity, but one also derives density and the speed of sound from conductance. There are sort of two primary methods to measure conductance. There's electrode-based, where an AC voltage is applied across two electrodes and we measure the current, or inductive. RBR uses inductive technology where an electric field is induced in the water around the cell and we measure the conductance of that volume. In the inductive conductivity sensor, it consists of two coils here, as we show. One is the generating coil and the other is the receiving coil. The way it works is an oscillator sends an AC signal to the generating coil, which induces a magnetic flux and induces an electric current in the seawater surrounding the cell. This induced current then flows through the receiving coil and causing a secondary current in that. And this is what we measure. And the current in this receiving coil is inversely proportional to the seawater. And I have an example of one here. This is what our inductive conductivity cell looks like. Note that the thermistor is located quite close to the cell. And this is so that as it's profiling through the water, this particular one is streamlined, so it kind of flows nicely through the water as it's being profiled. But this location of the thermistor to the sort of inlet of the conductivity cell is very important because we want to make sure we are measuring the exact same parcel of water so that our temperature and conductivity reading are very nicely matched. Oh, and it's a pretty robust design. So it's mostly susceptible to macro fouling. Any micro fouling of sort of small films or whatnot doesn't really affect the measurement because it's actually measuring quite a large volume of water around the cell. It can extend up to 15 centimeters away, this sort of sphere of measurement, with the bulk of it sort of around 80% happening within the cell and then the remaining 15 in the volume around it. So as I mentioned, Fouling is a problem for both technologies. For electrodes, you can have microfouling on the electrodes, which will cause a change in their ability to measure the conductance. That can be mitigated by using a biocide or something inside the cell to block any fouling. For an inductive, it's more of a macro fouling. So we talking like large growth of algae and mollusks. And that can be mitigated by using UV lamps. So basically irradiating the surface with UV to stop the growth. For an inductive conductivity cell, it uses quite a bit less power than electrodes. One, because you don't have to run a pump. So there's a lot less power there. So about 90% less per sample. And because you're not running a pump, that means it's a very quiet sensor. So it's ideal for kind of acoustic and turbulence projects. Next up is oxygen. Oxygen is consumed by living creatures, and the amount of, and so that's particularly why we measure it, but also the amount of oxygen in the water can tell you kind of the age of the waters and help distinguish different water masses. There's two primary methods for measuring oxygen. One is optical, which uses an organic molecule as the sensing element, and the other is galvanic, such as a Clark cell. And this cell, it generates current as it consumes oxygen. So oxygen moves through a semi-permeable membrane and then goes through a chemical reaction to induce a current. For oxygen optodes, they work by a mechanism called luminescence quenching. Most optodes use the same molecule for sensing, which is this platinum acetylethylene perforin complex. So it's unique in that it can absorb light, and so when you bombard it with the right wavelength of light, it enters an excited state. And if it's just left there to its own ability, it'll then re-emit more light. However, if oxygen is present in the environment, the oxygen then collides with a molecule in its excited state, and then the energy is transferred to the oxygen molecule, and then there's no emission of light. And so what we measure is actually the quenching of light from the foil. So we bombard it with light, we look at the light coming back, and how quickly that light disappears is proportional to the amount of oxygen in the water. So as I mentioned, all of the optodes that RBR manufactures uses the same complex. And here we have three different varieties. They have a bit of a physical difference for the slow, standard, and the fast, where the slow has an additional black coating, which prevents the active film protects it from ambient light, so it doesn't get bleached. But also it provides the ability for it to be wiped. So any biological growth on the surface can be cleared by a simple wiping brush. It's also, because of this additional membrane, it makes the signal very bright, which allows us to have a dimmer LED, and thus it consumes less power than sort of the standard sensor. In the case of the fast, it has a very thin coating, and it actually has quite a unique construction. And the time constants are kind of shown below here at the bottom. So I have a couple examples of the sensors here. So this is the slow, as I pointed out. So with its black sort of Teflon coated membrane, this is ideal for any long-term deployments, and it's very stable because lack of any light being able to bombard it. The fast is what we have here. As you can see, it's got this pink coating. Our fast has a kind of a unique construction. So typically to have a faster responding sensor, what you want is to have a thinner deposit of your active molecule, because the time response is mitigated by the diffusion of molecule through the active film. So to make the sensor respond faster, you make a thinner film of the active complex, and thus you get a quicker response. But by having a thinner film means that you have a lot less of the molecule, and so the signal is quite a bit weaker, and so you have higher noise and less sensitivity. This particular foil has quite a unique construction. The way the luminophore is packaged into the foil, it's kind of packaged in this small molecular structure, which means we can put quite a few of the molecules in there. And to increase the signal, we embed a nanoparticle in there, which increases the scattering effect of the light, giving us a quite a bit stronger signal than most other fast sensors. So in fact, this one actually has a comparable sensitivity to that of the slow. So a very unique construction and a very good sensor there. So here I'm just showing an example of what happens when you take the 3 different varieties of our sensors and do a step change. So here I'm going from 260 micromole oxygen water down into 80 micromole water. And you can see the yellow trace here is the fast. Within the first sample, we've done the bulk of the change, and we're more or less reach our 80% within just a few seconds. The regular takes a little bit longer, and the slow is quite a bit longer, taking on the order of 30 seconds to reach the concentration. So next, for turbidity and backscatter, we measure backscatter and turbidity to know the abundance and distribution of suspended particles. This affects how far light can travel through the ocean and how much sediment is being transported. RBR offers a variety of backscatter and turbidity sensors. I have an example of 2 here. One is the C-point STMS, and the other is the RBR Tridente. And I'll use these 2 as kind of examples of how to describe the measurement technology. So how do we measure backscatter? So the sensor is constructed to have an LED, which illuminates a parcel of water at a defined angle, and a photodiode where its field of view intersects this LED beam. And sort of the intersection of the 2 creates this sample volume. And when a particle enters that sample volume, it scatters light back to the photodiode. And I'll show an example of one of these here. So here I have the Tridente. Might be a little difficult to see, but this middle channel here is for backscatter, where you can actually see the LED through that window there. And so it's emanating a cone of light in this direction, and the photodiode is looking at from another angle. On the photodiode side, we have a filter to select for only the LED wavelength of light that we want, and thus blocking anything else in the environment. And for this particular construction, we have the angle such that the LED is emitting light, and any particle would have to reflect that light at 120 degrees for it to get back to the detector. And these 2 cones, the cone of the LED beam and the cone of the field of view from the photodiode, make a sample volume that's about 1 milliliter in total. So here's a kind of a depiction of what we end up measuring as particles in this sample volume increase. So as the particle density increases in concentration, the current that we're getting back on the photodiode also increases in a linear fashion to a particular point. At some point, going the wrong direction, the current starts to deviate from this linear path, and this is a bit of a kind of a unique problem. So, and why does this happen? So essentially the density of particles in this volume becomes so high that it actually the particles start to block the light that's being scattered off of one particle from reaching the photodiode. The C-point has a unique method to get around this, where it adds a second photodiode at a different angle and at a much steeper angle. So this increases the linear range, but it does change the sample volume and kind of reduces the resolution. But if you want to measure turbidity in the thousands of FTUs, this is the tool to do it. So next up is fluorescence. There are a variety of fluorometers out there, and they measure fluorescence for quite a few different applications. That could be following a tracer such as rhodamine, looking for organic molecules, or identifying and quantifying photosynthetic organisms. The fluorometer I have here with me is the RBR Tridente. It has 3 channels, this particular instrument, with 2 of them dedicated to fluorescence. And it can accommodate a variety of different parameters. The measurement is quite similar to that of backscatter or turbidity, where we have an intersecting beam from the LED and a field of view from the photodiode. And so when a molecule or cell enters the sample volume, gets excited by the light emitted by the LED, and then that light is then fluoresced towards the photodiode. There are a huge variety of different compounds that one can measure with a fluorometer. In principle, you always excite a molecule with a short wavelength of light, and then that molecule re-emits that light after it's kind of consumed some of its energy at a longer wavelength. So for example, there's chlorophyll A here. It can be excited with light around sort of 440 nanometers, and then it emits light kind of closer to 700. Yeah. Which is in the red. Another parameter what people look at is dissolved organic matter. There's a huge variety of molecules that fluoresce. And here we have an example of an excitation and emission matrix showing quite a few of the different dissolved organic molecule compounds. One thing to note is that much of these molecules require excitation deeper in the UV, as you can see here. Some of these peaks are excited down at sort of 300 nanometers. Yeah. So one thing that's key and for the with the Tridente is that we use a material for the windows that does not fluoresce, and the construction is such that we'll see if I can get the angles just right. But on these particular channels, you can see there's filters on both the LED side and the photodiode side. And this is because we want to ensure that we only emit light in that narrow band that we want to excite the molecule with. And this is because quite often LEDs have emission that's outside of the wavelength that's specified. And because we're detecting such weak fluorescence signals, we want to make sure that we don't have any of this out of band emission from the LEDs, because it'll end up polluting our signal. And that's also why the window material choice is quite important. We selected materials that don't fluoresce because if the material is being fluoresced by the light that we're emitting, it then can pollute our signal when it comes back to our detector. So our last parameter we have to talk about today is both photosynthetically active radiation, and which is the band of radiation between 400 and 700 nanometers, and narrower wideband radiation, which typically is within this 400 to 700 nanometer range. We primarily measure PAR and other wavebands to see what available light is present for organisms in the water column. But some researchers will also use the attenuation of particular wavelengths to tell them what other particles could be in the water column above them. So how do we measure PAR and other radiation? It's fairly simple. I have kind of a simple depiction of it here, where we have light entering the face of the sensor through a diffuser, and then it passes through this diffuser, and then we have a filter inside to select the particular wavelength or waveband that we're interested in, and then a photodiode to measure it. There's sort of two primary constructions for a PAR radiometer. One is called a cosine, such as the RBR Coda, PAR, and RAD. And this is designed primarily for directional measurement and is used for measuring upwelling or downwelling radiation. Another construction is spherical, which I have here on the right. And this is an example of a light core sensor. And this is equally sensitive to light in all directions. And this kind of is to mimic a cellular organism. So, and as it's ideal for photosynthesis, for measuring light that's available for photosynthetic organisms. For the cosine sensors, and I guess other sensors in general, there's sort of two main performances that one wants to look at. One, the spectral response. So we want to make sure that there's a sharp cutoff outside of the wavelength that we're interested in. And the other is the cosine response. So for the cosine sensors, you want the sensor to have a known angular dependence to the radiation. I have one of the RBR codes here that I can share. So the spectral response is obtained by the selection of components for the sensor. So ensuring you have a high quality filter to select just for the particular wavelength you want and has a high out of band rejection. And also making sure that you have a good photodiode that has a nice flat response across the region that you're interested in. The cosine response is driven by the construction of the face here. So everything from the height of that diffuser, the little white piece in the middle, and the gap of this, what we call the moat between the diffuser and this lip here, and even the chamfer on this edge affects how the sensor performs as the sun or the light source kind of moves around the sensor. And that's how we get that nice cosine response there. And I think that is it for the slides I have today. Thank you for joining today's webinar. Recording will be sent to you by email shortly. And I think we're ready for some questions now. So first one is from Kelsey. Are the optical oxygen sensors putting out a beam of light, or are they relying on ambient light? So yes, I don't think I touched on that. So yes, there is a, oh, here, I'll stop sharing so I can show the optode. So yes, inside there is an LED that is shining on the back of this membrane here. So it's we have a piece of glass and then the membrane sitting on top. And so the oxygen diffuses from one side, and from the other side, we hit it with an LED. And then we measure the light that's being fluoresced back to the detector. So one thing some manufacturers do is you always want to compensate for other lights. So you can hit it with another wavelength of light that the membrane's insensitive to. The RBR's construction is such that we use two LEDs. One is just dedicated to the reference. So if the LED intensity changes over time, we want to make sure that we measure that, and that so that mitigates the drift, some of the drift of the sensor. So in our construction, we have one LED that shines directly at the film, and another LED that just shines onto the photodiode. So we do two measurements, one with the LED bombarding the foil, and the second one where we just see the one that's internal. And so the two LEDs will age at the same rate, and their power output will change proportionally over time. And so you can do a nice compensation there to ensure that you don't have drift on your sensor. Another question here about backscatter measurement. The 1 milliliter sample volume sounds so small compared to the volume of the body of water. I'm assuming the turbidity is generally pretty constant through the water column, so that taking a big series of 1 millimeter measurements is sufficiently accurate. Yes, so actually that's exactly right. So we are doing quite a bit of measurements. So this particular sensor operates at 32 Hertz. And so that 1 milliliter volume is quite small, but it's being flushed constantly. So as this thing moves through the water, it's doing at 32 Hertz, it's basically measuring quite a new parcel of water quite rapidly. So it's quite, I think it's ideal to have it in that construction. Another one for turbidity and backscatter, is turbidity the only output? Can the sensor be calibrated to produce volume scattering function? Yes, it can, certainly. So That is something we'll work towards, to doing a proper volume scattering function. We've talked a lot with various scientists to ensure that we have the optics designed such that we can do a nice characterization of the volume scattering function and calibrate it accordingly. So that'll certainly be available in the near future. Yeah. Any other questions out there? All right, well, if that's all, thank you all for joining us. We can also curate some of these questions. Oh, one more, certainly, not a problem. So Kelsey asks, I work for AGO Environmental. We make winches for deploying oceanographic equipment. Can you share info about stuff like how fast these sensors need to be pulled through the water column, what kind of cables they work with, etc.? Yeah, so certainly our cabled sensors, so this particular sensor and all of our CODA series, they communicate over RS-232. Over a variety of baud rates, depending on how far you want to send that signal and how fast you want it to sample. As for rates, that would be mostly driven by the time response. So if you're working with a CTD, the conductivity sensor, it's a flushing action. So, you know, it can sample up to 32 hertz as well. So as the volume of measurement is being flushed, it's responding almost instantaneously. The parameter you'd want to look for is the time response of the thermistor. So this has a 100 millisecond time constant. So if you are in an environment with very sharp thermoclines, you would want to adjust your speed so that you can resolve that thermocline. So we don't have sort of a hard, fast value for you, but I think taking into account the time response of your slowest sensor and how sharp of gradients you would expect in that environment can start to give you an idea of how quickly you'd want to be profiling through that region. So Xiaodong asks, I see you have radiance sensors. Any plan to make radiance sensors? Oh, I'm sorry, I'll have to follow up with you on that one. I'm not too sure what you mean there. Yes, and Frey asks, what influence has depth pressure on other sensors? So it's a great question. So the oxygen foil on the dissolved oxygen sensor has a sensitivity to pressure. They've been characterized both at sea as well as in our pressure chamber. They have an effect of about 3% per 1,000 decibars. So whatever environment you're in, there's a pressure compensation performed on any RBR loggers. So if you have an RBR logger with an optode, the oxygen readout on that unit will take the pressure reading from the logger and compensate your sensor's reading. Likewise, if you are just working with the sensor alone, you can input a static pressure to compensate the value. But that's only one specific value. So if you want to do dynamic pressure changes, you either need to have an accompanying logger with its own pressure sensor, or you'd have to do your compensation in post-processing. Xiao Dongjiang, what is the depth rating for the turbidity and backscatter sensor? The Tridente is rated to 2,000 meters. We're working to get it to be rated to 6,000 meters. That's our goal. As for the C-Point STMS, that's a 6,000 meter rated sensor. And next, do the sensors from Flora, do the sensors operate for both fresh and seawater? So yes, all of the sensors can operate in fresh and seawater. For example, the conductivity cell, it can measure quite low conductance water. So it can perform across that full range. The oxygen optode, so the measurement of saturation is independent of salinity, but concentration is dependent on salinity. So just like the pressure, if you have a conductivity sensor and are measuring salinity and you integrate an optode onto a logger that also has a salinity sensor, it will do the compensation there. And just like pressure, if you are just operating with the sensor standalone, you can input a static salinity value to do the compensation on board from the output of the sensor. Other sensors, I don't believe, have a strong dependence on salinity. Yeah, I think it's just that optode. All right, any other questions? Okay, thank you very much, Xiao Dong. I'll be happy to follow up and clarify on that one question I wasn't able to answer. All right, well, thank you very much. We will also curate the Q&A on some of the common questions and provide those as well. And if you have any further questions, please visit our website or email us at info@rbr-global.com. All right, thank you very much.